And we are live. Sort of. There we go. All right, so this is lab number 2. And the idea behind the lab is that there's code backing the lab. So has everyone had a chance to look at the code on GitHub for the Lisp?
A little bit, yeah.
You haven't. Okay, so let me go to the GitHub page. So it's github.com. Let me Michael O. Church Summer 2015 Haskell class. And so Lisp.hs is the main module of this program. I'm going to be going through it in the slides. There's a pre-video where I do some work with this. It's on YouTube. I just call it pre-video, where I do some work with this Lisp and show how it works. It's just a very bare bones Lisp. And the main file is lisp.hs, and then there's a directory called Lisp, and it's got all of the modules that support it. So yeah. So just to give an indication of what's to come, man plans, flying spaghetti monster laughs. Lab 2 is going to be the Lisp Parser and the reader. The Lisp that I wrote is 2 labs worth of material to cover all of it. Monday, the 10th, there's not going to be a class because I'm a little bit behind and I just want to catch up, and I know a lot of other people need time to catch up, so it just seems prudent to take a break. The 12th, I'm going to cover foldable, traversable, some of the more advanced type classes, may get into multi-parameter type classes and how those work. Reminds me I need to cover language extensions in one of these lectures, possibly number 10. But number 9 is going to focus on lenses. I'd like to say that I can cover that in an hour. That remains to be seen. But we'll get into what they are and how they work and why they're useful. The 19th is another lab, which is the second half of the Lisp that is written in Haskell. The 24th is lecture 10. I realized that I haven't done file I/O in much detail and system programming, and I think that's useful enough to merit some attention. I might also throw the language extension stuff in there because I don't think that that's a whole hour. Lab 4, I'm going to do a web service in Haskell just to show you some Haskell web stuff. The 31st of August and the 2nd of September will probably be concurrency in Haskell. I'm guessing that'll be 2 lectures. I'm not really sure. I haven't planned it out yet. But there's a lot of cool stuff. There's software transactional memory, which is nice. That alone could be a lecture. You know, concurrent Haskell, there's a whole book on it, which I will recommend highly. It's called Parallel and Concurrent Programming in Haskell. It's great. After this class is over, if you want to continue your Haskell edification, read that. And probably for the 9th, the 7th is Labor Day, but on Wednesday the 9th, foreign function interface maybe. I'm not really sure because I've never actually used the FFI. So there'd be some research there. And yeah, so that's sort of what I'm looking at for the next month. I figure I'll be wrapped up probably around the 23rd of September. And if you have requests, recommendations, please let me know. You want me to cover something, I'll look into it. May have to do some research beforehand, but certainly, you know, I'm open to requests for the end of this class. So are there any questions that arose out of the Lisp and Haskell that some of you have looked at?
I haven't gotten enough into the code to really have valid questions. I think, like, I guess I really haven't understood enough of the code.
Okay, that's fair.
Have valid questions.
That's fair. I mean, it's a lot of stuff, and the thing about the labs is it's kind of going into the deep end because there are a lot of things going on at once. Does everyone feel confident that they know how to look code up? Like if you see a function name and you don't know what it does, do you know where to look?
Oh yeah.
Okay. I mean, there's, do you know?
Yeah, there's Google, right?
There's Hoogle. There's also a resource that I found quite useful is Stackage. It's from FP Complete. And assuming I can get online, they have their own Hoogle, which is more extensive. It covers more stuff. And when it's online, it's great, but it's not. I don't think I have an internet connection right now, which could be interesting.
Mine dropped. And then I
Okay.
connected.
Well, no, never mind. It's back now. Okay.
All right. So one of the first places to look in a Haskell file is the .cabl file. There is a replacement for cabl called stack. I have not looked at it yet. That may be another thing that I do before the end of the class. But for now, we'll just focus on cabl. And this is what the block about Lisp looks like. So first, we're declaring that Lisp is an executable as opposed to a library. That means that we can run it with cabl run Lisp. You can also use cabl REPL Lisp to get an interactive session that loads that executable. I did that a lot when I was debugging it. Main is, that tells you where your main module is. Perhaps slightly confusingly, there's a main action. It's an IO unit, so I've been calling IOs actions. To avoid using the word function. And then there's the capital M main, which is the module, which is what, and the main.main is the entry point into the program. Most modules start with import statements. So as I look through lisp.hs, or as you look through it if you have the code, you'll see a bunch of import statements. First, we've got the standard library, control.monad, and so on. And then we have all the Lisp stuff that is specific to this project, like lisp.builtins, lisp.evaluator, so on and so on. The one thing I'm going to show is command line arguments. So get args from system.environment returns the command line arguments. And of course, because it's dependent on the system context in which the program's running, it's in the IO monad. And we fmap not lm, no prelude to determine whether we're using the prelude. The prelude is a Lisp file that the Lisp that I've provided executes before it does anything. If you use no prelude, then it will just do a very minimal environment called init-env instead of the with prelude environment. The next thing you'll see is GHC options. -w all is turning all the compiler warnings on. And -o2 is, I believe that's the maximum optimization level in Haskell. I don't think there's an 03. Build dependencies with version bounds. Yeah, what's up?
Is O2 optimizing the speed of the compiled, like the actual compiled bytecode or code or however? Question: is it optimizing the compilation step or the actual build?
It's optimizing the quality of the executable code.
Thank you.
So your compile will take longer, but it will run faster.
Okay.
Or it may take longer, I should say. I don't know that for sure. It probably takes longer. It's probably doing more passes.
So it's building a better optimized executable at the end of the day.
Exactly.
By doing O2. Okay.
Exactly. Some of the things you lose with optimizations are debuggability and if you have undefined behavior, which isn't really an issue in Haskell, but if you're using C, FF5, then
Oh, okay.
but I wouldn't worry about that.
Yeah.
So yeah, we declare the executables dependencies. We give it version bounds. Usually what I do is just I take the current version and say it has to be at least this, and that usually works. There's also cabal freeze, which will give you specific exact versions. That's if you want to freeze your versions in time and say, okay, I know that I've tested it with these versions, and that's what I'm going to put in production. And then the default language statement, don't worry about that. Just put Haskell 2010. There's also Haskell 98, but that's obviously out of date. So Haskell 2010 is the most up-to-date version of the language. The project structure that I have and the module names are generally mirrors of each other. Lisp built-ins.hs is lisp.built-ins. The only one that's different is lisp.hs because it's an executable. It has to define a module called main. If I called the module Lisp, then when I try to build the executable, it would say I can't find module main, and it would be an error. So the core of Lisp is the Lisp REPL. And as I showed in the video, if you want to run it, you can use cabal run Lisp. And you may also want to useledit so that you can use your error keys in the REPL. So today we're going to focus on the read component of the REPL, the parser, and the process of interpreting an S expression of Lisp form. It turns out that just doing that, we're going to cover a lot of topics that are important to us. So first, let me say that Haskell's got two parsing packages. One is called Parsec, and the other is called Parsec, which happens to be about 1.5 inches long. The first gives you more useful error messages, but it's not as fast, and it's oriented toward parsing general streams, usually a string or a text in data.txt, which is comprised of chars. The latter one, Parsec, is designed for speed and for handling binary data. So when you're dealing with a language that you've built, you probably want to use Parsec because if you have users, you're going to have user errors. Whereas if you're working with, say, 2 gigabytes of log data, then Parsec might be a better choice. So they're both parsing libraries and they're similar, but they have different strengths. If you look at Lisp.Parser, that module, you're going to see that some of our imports are followed by a parenthesized list of names. Some have hiding, and some also have an import qualified. And those are tools that we use to avoid namespace collisions because quite often all the good names are taken. For example, if you import data.txt, which is the recommended string type for anything more heavy duty than a few hundred characters, then you import data.txt without some kind of qualification, you now have ambiguity in map because there's a data.txt.map and there's a map in the prelude. So one of the ways that we get around this problem is that we will import a library and say, I only want these names. Data.char, I only want is space. Then we're not importing anything else from data.char. With hiding, we're saying, I want to import everything with these names. And in this case, I use it to avoid importing text.parsec's legacy applicative functions because control.applicative is now mainstream and there are more general definitions of many and your choice operator. The choice operator is actually for alternative, not applicative, but you know what I mean. Right. And you'll see this a lot, and it's very important. You can import qualified. And what that gives you is it gives you a shorter name. So you can say if you do import qualified data.set as S, then you can just use s.map for the map that's in data.set. And many of the modules are designed to only be imported qualified. And they might compete with the prelude for names. So, keep that in mind. If you see, for example, if you see a map defined by a module, then it's designed only to be imported qualified.
That makes sense.
Yeah.
I don't want to override the base map, dude. Right?
Well, Haskell will tell you when you've done it, it will complain.
Oh, really?
Yeah, because the prelude is just another module.
Okay.
You can actually not import the prelude if you want. There's a language extension for that.
Interesting.
But Haskell will tell you if it's ambiguous at compile time. It's not going to like silently let you
It's not Perl.
do the wrong thing. Exactly. It's not Perl. It's not like many other Java or dynamic languages. I think JavaScript has that problem. I'm not sure. Anyway, I'm not going to talk about JavaScript because I don't know much about it, and that's probably a good thing. No, it's not. It's never a good thing not to know something. But anyway, the S expression type. It's either an atom with a string or it's a list of S expressions. So this is just a tree of strings, and that's what the parser is going to return. It's AST-like because Lisp has a very simple syntax, so there's not a lot of parsing to do. And for now, we don't care about interpreting any of it. So if we see a 5, it's S atom string 5. We'll deal with what it is later. Now the parsec type is the type you're going to see a lot if you look at the parser. It's got 3 parameters, and 2 of them don't really matter for now, which is a good thing. Parsec SUA, it's a parser with stream type of S, and what they call user state of type U. That's if you want your parser to be stateful, you can create parsers that have some kind of state, and then when you combine parsers, that state will be threaded from one to the next. But we don't worry about that, so we just completely ignore it. And A is the return type. Of course, this is a monad in A, so that's parsec SU is essentially a monad that has state of type U and consumes a stream of type S. But S is always going to be stream, and our parsers are stateless aside from the consumption of the stream. So when we see parse atom and we see this collection of symbols, what does it mean? Well, we have S atom F map, so we're F mapping the S atom constructor over sum. Remember that sum takes a parser and returns the parser that will parse at least one of that thing. So it's like the plus in a regex. And then we have satisfy, and we don't know what satisfy is. And we can look it up, or in this case, I'll just explain what it is. It takes a Boolean function on chars, and it returns a parsec. That should be parsec, not parser. So let me fix that. String. The U just means that it will work for any type U. So it's completely agnostic of whether there's user state at all. And it returns a char. So satisfy F is a parser that if the leading character on the stream, if F of that character is true, it consumes that character and it returns it. And if it doesn't, then it fails, doesn't consume anything. And all of these parsers can look at the next character, but they don't generally look ahead, or at least that's not the assumption. So yeah, I'll get into look ahead in a second. So in this case, what does this parser do? Well, it collects some characters, so at least one, that is not white space, as you can see from the not dot is space dot being the composition operator, and it's not a special character. And the special characters are the open and close parentheses, the quote character, and the semicolon, which delineates a comment. And just to recall, parsers are monadic, which means they're also functors and they're applicatives. So we can fmap a parser, we can use the applicative brackety splat, snowflake, app, whatever you want to call it. All of that stuff's available to us.
Can you go that real quick question?
Sure.
Go back to the function you specify there. When you do function composition, why is the dot operator infix and not postfix? Right?
Okay, you mean not prefix?
Yeah, it's not, or yeah, rather prefix. Yeah.
Okay, so Haskell convention is that if it's alphanumeric name, it's prefixed by default.
Mm-hmm.
And then if you want to use it infix, you have to put it in back quotes. So like when I use not lm as infix, then I have to put back quotes around it. The punctuation operators are by default infix, which means they have like an order of operations policy. You can use them prefix by enclosing them in parens. So, because I mean, I assume, I don't know if you've seen this in Haskell, but you know, if you do, that's the same as 4 plus 5.
Right.
I cover infix in some of the earlier lectures, which you
Okay. I
You'll
missed
see.
those. Yeah.
yeah, those are on YouTube. So
Okay, I'll check that out when I get home. Thanks.
okay, cool. Yeah, it's a little confusing, but once you get the hang of it, it makes sense. So some other useful parsers, and from here on out, I'm going to use the type synonym parser A to mean parsec string UA. So that's, you know, just factoring out the stuff that doesn't change for our purposes. Because parsec is a general parser. It's not, it doesn't parse only strings. So char is a parser that parses exactly that character. And if it sees something different, then it fails. So we can build that using satisfy. I don't think it's actually built under the hood using satisfy, but it could be. And one of is similar, except it has multiple alternatives that will pass. So one of, and then you give it the string AEIOU that matches a vowel and returns the vowel. We also have a string parser, which matches a whole string. So we recall the choice operator, which allows you to choose between two parsers. So then the question is, what behavior are we going to expect from this parser down here? If we give that parser the string cat, what do we expect?
Gonna char is the parser, the character parser, right?
Right, and string matches a string. So we build it by mapping the character parser across the string.
The brackety pipe is the either or, right?
Yeah, it's the choice operator.
So you just get the true.
We get the first alternative. So it returns,
Parser of string.
right, so it's a parser of string. String, so what does a parser of string return? It returns a string.
Yeah.
So that's going to return the string cat. And what do you expect if you pass in the string cow?
Also.
Well, that's where you're
yeah.
wrong.
Oh.
And this is frustrating and a little bit unexpected. And it's just a quirk of how Parser thinks about parsing. There's sort of an unexpected state effect, because when you give it the string cow, it will match the C, And so it'll go down the first branch or the first alternative. And then it gets an O, and it says, well, that's not an A, and I don't know what to do with that. So the choice operator commits as soon as it consumes input.
Oh.
And there's a reason for that, and I'll get into what that is. Before I do that, there's the function parse. That's how you use a parser, and that's an intimidating type signature. So let's simplify it by specializing S to string. That allows us to take out that multi-parameter type class that we're looking at. And then, source name is just string. The source name is like the file that it's parsing. So if there's an error, that becomes relevant. And we have parser A, arrow string. That's the string being parsed, or the stream. Arrow the source name, which is also a string. For now, you can just pass in the empty string, and then it returns either a parse error or an A. Okay, so now let's try to WTF this thing that we found with the alternative, or the choice operator. So in Parsec, the choice operator is defined as try the first parser, and if that fails and you haven't consumed any input, try the second parser. If you have consumed input, you just fail. And that's really inconvenient and annoying, but the reason for that is because if you had any other policy, you would be mandating that every time there's a choice operator, you keep track of everything you've parsed. So you'd be mandating backtracking, and that would hurt your performance. So this case is not what it looks like, because you give it cow, it consumes a C, then it's committed to the string cat, and that fails. If you want to get around that, and sometimes you do, then you can use try. And try takes a parser and returns another parser that behaves identically but does not consume input on failure. And what I mean is if it's not consuming input on failure, then what it's actually doing is it's rewinding. So that puts backtracking into your parsing. The drawback is that now you have a parser that has to keep a record of everything that is consumed. It has state that is accumulating as it parses. So you don't want to put, like, if you're parsing like a gigabyte of data, you don't want to put that in a try.
I think I'm misunderstanding a little bit. What is the purpose of saying string cat or string cow? I know it's not the logical or, it's the, but why would you type that code?
If you want a parser that rejects everything other than the string cat and the string cow.
Okay.
It's an example.
Okay, I see.
But I actually got, I'm sorry?
No, I just needed some outer perspective, again, like basics. So.
Yeah. I actually got burned by a case of this in the Lisp code. So there was a bug that I actually just found a couple days ago. But anyway. So yeah, this is one of the things that surprises a lot of people. So I found it worthwhile to draw attention to it.
So like obviously adding that try block is reasonable in this extremely simplified scenario. We're only trying to match on cat or cow, right?
Well, try isn't a block, it's just a function. It takes a
right.
parser and returns another parser that has rewind.
Right. But if you were to try, as our language is going to grow in complexity, right? Are we just going to increasingly just like assume this decision tree with like try functions wrapping like everything, or are we going to eventually build like some sort of like decision tree that doesn't require like kind of iteratively trying every single possibility until we find the right one?
Okay, so the answer is you shouldn't use try often.
Okay.
Because when you're designing a grammar or when you're parsing someone else's grammar, if you have to know, so you're parsing a stream of tokens, which could be characters. If you have to look ahead 1 million characters to know what the character you're looking at now does,
It's impossible. You're never going to do that in a reasonable amount of time.
Well,
You wrote a bad language.
yeah, it's a design flaw.
Sure.
So in general, you should only use try when you need it. And most languages will be written especially programming languages. I mean, natural language is its own weird thing
Sure.
with its own rules.
I think like one character lookup is like sort of the standard what you're supposed to be able to get away with in most languages, and I think a lot of the modern ones
Yeah.
have forgone even that. Like,
Yeah,
like
Yep.
you can technically parse bash with no look ahead.
exactly. So, I mean, the answer is you shouldn't just wrap everything in a try to be defensive.
Right. That's that.
And yeah. So, in general, you should know which alternative you're going with by looking at the first character. Sometimes that is impossible. Like sometimes, you have to look ahead more than one character, but it should always be a fixed amount. You shouldn't be building arbitrary look ahead into your language.
So
Or
on
your
a
parsing.
token by token basis, like I guess when I think about like the process of typically taking a programming language and then producing some sort of output, right? You're going to tokenize, then you lex, and then you parse, right? So like theoretically, if you've already got lexed tokens, you shouldn't have to do that much crazy stuff in terms of like look ahead, right? Within an individual token, it seems like that's pretty reasonable to look, 2 or 3 characters ahead, especially in Lisp. Most tokens aren't going to be longer than that, right?
Yeah, I only use try at one place, and the place where I use it is
I just sort of noticed that we never really talked about like lexing. We skipped straight to parsing, which not necessarily skipped, but
well,
is that just sort of like something we're not going to do?
the S expression parsing is combining the lexing, and the parsing is really minimal because in Lisp you don't really have to do a lot of parsing because you're essentially writing ASTs with a couple of caveats.
Okay.
All right, let me show this example. So the only place where I'm using try is when I'm inside a string literal, and I have to distinguish between the escaped quote character and the escaped / character. That's really the only time.
So it only needs to have rewind for basically one character is all you're saying. You're saying
Yeah,
like that in that time you're giving the parser capability to look one ahead and then go back if it has to.
exactly. And this could actually be rewritten without the try. Now that I'm looking at it, you could move. Could it? Yeah, I think this could be rewritten without the try, but it's not interesting enough to merit actually doing it.
Yeah.
So in any case, we also have set by and end by. Those take a parser of some kind of type A and a parser of a separator. And the sep type is just like, that could be parser B. That's just saying, some other type that I don't really care about. Like I run that parser for side effects, but I don't do anything with the result. And the set by would be, you give it, say, a field parser and a parser that matches the character, comma, and you have a CSV parser or a CSV line parser. End by is similar, except it expects the sequence to be ended by that separator as well. So an example of set by that we actually use is when we're parsing a list of S expressions. We're F mapping S list, that's a constructor, across this big parser, relatively big, which parses a left paren, the right biased, or the right biased app says we're throwing away that character because we're not using it in our return. Parses many space, means many space characters, obviously. Mm-hmm. And then the body, which is actually the only thing we return because we have a left biased app on the end of it. And then we're saying, okay, we parse a bunch of spaces and we parse a right parenthesis, but we throw those out. Then body is set by parse s expression. So there's obviously a recursion going on because parse list is a subcase of parse s expression, and the separator is sum space. So it's saying, parse an s expression, parse sum space, sum meaning at least one, and then parse another one until you run out. EOF is a parser that succeeds if it's at the end of the stream, and otherwise it fails. And since it has no meaningful return, it is a parser that returns unit. So this is, if you don't believe me, which you shouldn't, you should never believe me because I make mistakes. You can run cabal repl lisp, import the Lisp parser and text.parsec, and you can run the s expression parser and see what it does to this this Lisp form. So we're giving it a list with 1 and an A, that's a symbol, and then another list with a 2 and a quote B, and it parses it to be exactly what you'd expect. The one thing that may be unclear, but it makes sense in a Lisp context, is that whenever it sees a single quote following a symbol, it will wrap that symbol in a list where the first element is the symbol quote. That's just a Lispism. And finally, we have comments. Anytime it sees a semicolon, it says, okay, that's a comment.
I think you mentioned not having comment in the video that I saw. Is that something that you added since the video?
I added them a couple weeks ago, yeah.
Okay.
They're in there now because the prelude, I wanted to be able to comment things out and document things like a good person.
Okay, cool.
So the Lisp parser is really simple. It doesn't really care if it's given valid Lisp. It's just gonna build it into S expressions. But it groups together your parenthesized pieces, which means that it will check that your parentheses match. It ignores comments, continuing to the end of line. It handles string literals and the escape sequences, which we don't have many of. That's a good thing. And it has special handling of the single quote. And then the reader isn't that interesting. The two important functions are read S expression, which turns an S expression into a Lisp value. It turns out that every S expression has a meaningful interpretation as a Lisp value. And read string, which takes a string. If it can't turn it into an S expression, it's a parse error. Otherwise, it's a Lisp value. But we need to understand the types in this file, and they're all in types.hs. The first thing that you encounter is a terrifying language pragma, template Haskell. Template Haskell is Haskell's macro system. The only thing we do with it is we auto-generate some of the boilerplate accompanying lenses, so don't even worry about that. We're not going to be required to understand template Haskell in detail. The Lisp value type has a string type, LV string, that's a constructor. Another constructor, LV symbol, that under the hood is a string, but it's saying, okay, I know this is a symbol. A string is a piece of data that you can like operate on, whereas a symbol in Lisp is sort of this irreducible concept that maps to an atom of code. We have numbers, we have bools, we have list of Lisp values, so again, it's a recursively defined type, and we have LV function, which wraps a Lisp function, which actually covers 3 cases of functions. So the lesson here, and why I built a Lisp for this exercise, is because obviously we have a lot of people coming in from dynamic languages who are afraid of what they're going to lose if they go to a statically typed language, and the answer is pretty much nothing because you can build in as much dynamism as you want. The only thing you lose really is that you have to know in advance how much dynamism you want. In this case, we're saying, yeah, our Lisp has strings, it has symbols, it has numbers, and it has functions, and we're unifying them all to this type Lisp value, but we don't have a universal type.
So you couldn't make your own type.
I'm sorry?
You couldn't define a type in Lisp. In the Lisp. Like.
Well, this Lisp is untyped. It's an untyped language. It has minimal runtime type checking, but it's untyped really. Or it's what we call unityped. It has one type, everything is a subtype of. So Lisp function has 3 cases. LF primitive is for the built-in stateless functions like adding, subtracting, and they can throw an error. So first of all, they have variarity, so they can take a list of Lisp values, and it will either return some kind of error or it will give you a value. LF action looks similar, except it's in the Lisp monad. LF action is for the built-in actions like printing things to the console and loading things from a file, which is incidentally the only I/O we really do. And then LF closure is for code, or for closures. And I'll show an example of that. So here's LF primitive. I discussed that. It's for a function that might fail, but other than that, it's stateless. LF action uses the Lisp monad to say that it can perform I/O, it can have stateful effects. Stateful effects on the state that is internal to the Lisp context. So the Lisp monad is built using monad transformer stacks, which is why I taught it. We have an accept T Lisp error of a state T Lisp env around a base monad of I/O. Lisp error is just a thin wrapper around Lisp value. We're essentially just designating it as, this value was thrown as an error or an exception rather than typical return. Lisp env is this type here. It's got a stack. It's got globals. Lisp frame is a map from strings to Lisp values. It's got a gensim counter because gensim is a function that just generates a new symbol that has never been seen before. So it has to be unique. So here we have it auto incrementing. And then macros, which is a list of what is recognized as a macro at a given time. And these are prefixed with an underscore because we want to define lenses, which I'll be covering in about a week. So don't worry about that for now. So here's a question. What is the difference between accept T Lisp error and state, or between the Lisp monad that we have and this one on the bottom where I have the state T on the outside? And I don't expect anyone to be able to work it out in their head. Just give me a guess as to what you think it might be, like what the difference might be.
It's a hint.
Give a hint, yeah, like a hint. It probably has something to do with like what can modify, like what state is internal to which monad and what can make modifications to like the state that you care about modifying. Okay,
so let me try for a hint. With accept T, you're adding the capability to fail. And with the state monad, the state T transformer, you're adding some notion of state. What are 2 different ways in which those can compose?
You can have failed state or a state of failure.
Okay, that's sort of it.
I just literally put the words. You asked me the 2 ways those 2 things.
I actually think those are the same. So I'll give the answer because these are actually annoying to work out on paper. So if you work them out on paper, and one way to do that is to, at the console, just start unwrapping the monad and seeing what type you get. You use like the run accept T and the run state T, the inverses of the constructors. We find that the Lisp monad that we use with accept on the outside allows the environment to change even when there's a failure. So it takes a Lisp env, and through the IO monad, it returns an either Lisp error A and a new environment, which means that it returns a Lisp env even when there's a failure. We have state T on the outside. We're returning either a Lisp error or an A in a new Lisp environment, which means that we're saying that in the second example, the Lisp environment doesn't change when there's an error. And we want the one up top because we might decide later on that we want our Lisp state to keep track of how many errors were generated or something like that. Or maybe we want a last error function where it will, the REPL allows you to say, okay, give me the last exception you threw. So we want the one up top. And finally, we have LF closure as the third case of Lisp functions. It's got a name, that's a string. It's got a stack to capture local variables, which a closure has to do. That's actually a design mistake on my part because it really, it doesn't need to capture the whole stack. It just needs to capture the most local binding or the highest binding on the stack. It's got its parameters as a list of strings, and it's got a body. And the body is a Lisp value because that's sort of the idea behind Lisp is that code is data, data is code. So when we have this lambda expression, we give it the name add, two parameters x and y, and the body is the form. So that's a piece of Lisp. It's a Lisp value, and it's a list that has the symbol plus, the symbol x, and the symbol y. And at the runtime, it will resolve all of those and say, oh, I want you to add the x and the y, where the x and the y were the parameters or the arguments passed in, and the plus refers to the built-in plus. So that's something we'll cover in the second half of this lab, the one that'll be in 2 weeks. Finally, sets and maps. Those are important, and I realized at this point that I haven't really covered them yet. So first of all, you almost always want to import them qualified. You have sets in data.set and maps in data.map, and they will collide with your prelude if you don't import them, if you import them wholesale. So you almost always want to use import qualified and, call your data.map, say, M. And they've got rich APIs. I can't cover all the functions. You can look them up. I'll just cover the ones that I find to be most important. So for set, well, you have empty, which is a set of A for any A, because every type has an empty set living in it. We have singleton, which constructs a one-element set. We have from list and to list. Those convert to and from lists, but they're not necessarily inverses of each other. Does anyone know why?
Lists can have duplicates?
Exactly. And the set is also going to order everything because Haskell sets are ordered binary trees, which is why there's an ORD constraint on from list.
Sounds sort of weird.
Wait, lists in Haskell are unordered?
Well, a list, the things in the list don't have to be comparable.
Oh, okay.
Yeah.
So the set must be comparable, and
Exactly.
it's not just
It's
ordered,
sorted.
it's sorted.
Right.
Right.
Sorted.
Because a list has an order, right?
Right, it's not
Like B
sorted.
before A. They have an index and they have a specific order, right?
Exactly.
Whereas this is a set is like B and A would always be A B. It can't ever be B.
Right.
Okay.
Yep.
Cool.
So we have insert and delete. We have a member function, which is a membership check. We have folder and we have map. And those are probably the most interesting set functions. But one thing I want to call attention to is that map has an ORD constraint. Folder doesn't. Some of these functions do have ORD constraints and some don't. The question is why?
Do you want to preserve ordering as you map it? Maybe.
Because it looks like fold R sorts. Or no, fold R. Sorry, forget I said that.
So the question was, why does map have ORD B? and fold R doesn't?
Yeah, why does fold R not have any ORed constraint?
Oh, well, because you get a set of one. You fold it.
So folding is when you take a collection and distill it down to one item?
Yeah, it's a reduce.
Oh, so
Yeah.
it doesn't matter. The order doesn't matter?
The
You get a set
order,
of one.
the order can matter
Oh, yeah, I can.
if it's not commutative.
Exactly.
But you're folding a set.
Now let's look at some others. Why does
Oh, because
M-
it takes a set. Why would you need it?
Oh, because the set is already,
already
like you
ordered.
said, the set is already in a specific structure internally. Does that make sense? So it's always going to be
Sure.
1, 2, 3, 4
It's
as the definition of a set?
You're close. So the only way, there's no way to, at least, I mean, I'm sure if you crack open the set module and play around with private stuff, you could make an invalid set. But a valid set, so let me back up. So you can create a singleton or an empty set in any type, that even if it's not ORed. But as soon as you start inserting things into the set, you have to do comparisons, so you need ORed. And with the fold, it's not building a new set, it's just taking a set. So it's saying, okay, this is either, if it's in an ORed type, then it's already sorted in some order. And if it's, but we don't have to change that order. If it's not, if it's a singleton or an empty set, then the fold is trivial. The reason why map has the ORed constraint is because it's mapping into a different type.
Mhm.
And that means it's building up a new set, which incidentally might be smaller than the original set. With a list, when you do a map, you're always going to get a list of the same size. With sets, you don't have that. You don't have
Well,
that.
So, wouldn't technically, seeing as a map implies a mapping, wouldn't you always be able to mathematically infer the order for whatever set, whatever type you mapped an ordered set into?
So the map, the function that you pass into map doesn't have to respect the ordering. You could be mapping. You could have a. You could. It doesn't have. So that's what you're. I think what you're hinting at is the idea of homomorphism.
Yeah.
That you want your function to preserve the ordering, but it doesn't have to.
How could it not? It puts them all where they were, and if it's a map from one to another, then like the new types, then you shouldn't be able to map into a new type that's ordered differently than the old type.
But you
totally
can.
Yeah, you
you
totally
totally
can.
can.
I get it, but I just meant like in terms of like.
That's why set's not a functor. That's why set.map is not an fmap, or it's not a legal fmap for functor.
Interesting. So it's gonna map and then sort, basically.
Yeah. So if it like
Yeah.
if you have like
I guess my question is, you need some sort of like transit for that operation. All right, this is getting off
But
topic.
you're building
you
up
need
a
a
new set.
transitory state, like unrelated to your map, so that you can then sort them later, and or sort them as you build a new thing, taking each element. Like you're not actually mapping. You're like iterating and building.
Yeah, I mean that's one
map.
way to think of it. I mean map can be represented as a fold, and in the case of a set, that folding might be folding things into the set that are already there.
I see what you mean.
So yeah, when you call map on a list, you're always going to get, the types change, but the structure is the same.
Yep.
With a set, the structure is dependent on the ordering, and when you're building up a new set using map, you could have a set with different structure. So, set.empty is ORed agnostic, but building up and navigating these trees requires ORed. Yeah.
No, I was waiting.
Oh.
Go back.
Okay. And so you technically can have a 0 or 1 element set of a non-ORed type, because there's nothing about set that says I can only be a set of an ORed type. But you can't do anything set-like with it. And the reason we have the ORed-free fold R, one of the reasons why we don't put an ORed constraint on it is, first of all, we don't need it. But second of all, it allows set to be foldable, which is something I'll cover in the next lecture. The next concept that's important is functional updates. So when we see insert and delete, the names suggest in-place changes, but if you're a Haskeller, you probably already have guessed that the original is not changed. So when you insert 5 into the set Q, Q is still the same set. Insert 5 returns a new set. And the question is, how is this performant? I mean, does that mean that you're copying everything?
You just do a pointer. You know what I mean? You insert A to BCD, you just have A, and then you say like A is plus
It's
this.
compiled. You can make anything for it. Like you just.
That's not true.
Yeah, that would be crazy and horrible, especially when things in Haskell are immutable, right? By default. How can this be?
I mean, the compiler would just keep track.
The
That's not. I mean, I understand what you're
Compilers
saying.
aren't that
Compiler
smart.
magic.
Compiler's not that smart. Like,
No.
I
Wait,
mean,
so
it
you're saying that
doesn't
it's not performant? That's what you're saying?
Yeah,
Or
it's reasonably performant.
it is. And
Yeah.
are you saying how is it reasonably
Yeah,
performant?
I'm just this is a fairly. If you haven't seen it, you probably wouldn't know it. So I can cut to the chase if you want.
Okay.
Yeah.
All right. So it's trees.
Yeah.
It's a binary tree, which means
Everything's always a tree. The answer is always. Remember, like, how good is you made performance? The answer is always a binary tree.
there's a book. I
And the
have.
compiler.
There's a book that I haven't read, although I should have read it, by Okazaki, Purely Functional Data Structures, that gets way more in depth into this than I can do justice. But the fundamental idea is that you share as much data as you can.
Mm-hmm.
So here's your set with 1, 2, 3, 4 in it. And if you delete 3, you don't have to copy the whole thing. So the blue node corresponds to the set that has 1, 2, and 4. And it's able to use the 1 and the 2 and the node connecting them. And it's able to use the 4. So you have to do a little work, but you don't have to copy the whole set. In fact, you're not copying any of the data. You're just creating a new node. Now, sometimes when you're deleting, you'll have to create multiple nodes, but it will always be logarithmic in the size of the set. Or if your binary trees are balanced, which is a solved problem. When you're inserting, we have a similar thing. In this case where we're inserting 5, well, we create a new node. I don't know if this is how Haskell would actually balance the trees, but in this particular case, we're creating a new node that its left is the node with the 3, 4, its right is the 5, and then we have a node for the whole map that, it shares the same left as the old node, and the only thing that changes is the right.
This would be slightly wrong, if I'm correct, because you would be modifying the previous set, right? When you remove the 3, I was a blue dot before, now it was just appended.
Okay, so the original set is unchanged. The original set still has the same meaning. That's the gray dot at the top.
Yeah, sorry, I might have like lost connections.
Delete 3 is a new set that shares some structure with the old set.
Yeah.
Delete 3 is delete 3 of that set. Right? So S could be pointing to. It's actually a little confusing, but S could be pointing to the apex, and then delete 3S would be pointing to the blue dot, the blue node.
Right.
And in this case,
This is insert 5S, right? From the original
Yeah.
tree.
yeah, if S points to the apex, then insert 5S would point to the green dot.
Oh yeah.
And so we share most of the structure, and by most I mean that we share all but a logarithmic amount of it. So if we have a million nodes and a depth of 20, we might have to alter 20 nodes, which is perhaps more than we'd like, but it's not O of n, it's O of log n. And in fact, if you use a different branching factor, say 32, then you get what they call effectively constant time, which is actually still logarithmic. But Scala's collections and closures collections they hash what you put into it, and assuming you have a good hash function, which is actually a pretty big assumption, but that's another story entirely.
Yeah.
Huge assumption.
Then you get much better logarithmic
Well,
performance.
then, don't you have to pay for the cost of rebalancing trees though at some point, as you kind of, apply more and more operations to these collections?
Those
Or are
functions,
those pretty reasonably performant operations?
I believe that there are tree structures that balancing is also log of n,
Okay.
or at least certainly amortized and probably worst case. Like I'm pretty sure there are trees that, I don't remember them because it was, more than a decade ago when I took data structures.
Yeah.
But it's a solved problem.
Yeah, that's sure. And so then you're just dealing with you're still in log n time. Okay.
Yeah.
Cool.
So data sharing improves the performance. We don't do a full copy. We only copy a logarithmically sized slice of it. Some other set functions. We have O of one size. The reason it's O of one is because the set stores the size at the node. We have union, intersection, and difference. Find min and find max. Those are not properties of mathematical sets necessarily, but they're properties of Haskell sets because they're trees. So those can be implemented and they're log time.
Yeah, that's super fast, right? Just go down one side or the other, right?
Exactly. So here's a question. Or not really a question, but we've talked about laziness and strictness. There are lazy collections, strict collections, and one might want to know, are the default sets and the default maps, are they lazy or strict? And the answer is that they're strictness in the structure, or they're strict in the structure. But they're non-strict in the values in them.
When you're talking about strictness and laziness, like in the context of Haskell, what does that actually mean?
Okay.
Evaluation, right? Effectively.
Yeah, I'm assuming that.
Whether it's evaluated.
I'm assuming that, but I don't know.
There's
So-
a lot on that in some of the older lectures.
Yeah,
Oh, okay. So this is look at the old lecture.
sure. But
Okay.
so technically lazy and eager are different from strict and non-strict.
Okay.
Lazy and eager are performance considerations of when something's evaluated.
Yep.
Strict means a function is strict if passing a failing value into any argument causes the function to fail. It's non-strict if that's not the case.
Oh, okay.
How
Yeah.
can you order not like values that aren't strict
Well,
if you haven't
that's
set that from list 1 to undefined prelude undefined?
so why does the one on top, why does that fail when the one on the bottom doesn't?
Because from list requires ordered values. It requires a list, right? Like that's the signature.
Wait. So what 3 undefined is that strict or is that not strict? Are
Okay.
lists strict or are they not strict?
Lists are not strict.
Okay, that's why. Because you're giving it 3
It's
lists.
It's got 3 valid lists. It doesn't care.
Yeah. If is bracket 3 undefined, is that a list?
Yes.
In this
It's-
kind okay.
yeah.
So you'll get 3 back, right? You'll get a list of 3 back if it's not strict. Is that correct?
So basically, when something is only strict if it's recursively strict. Like in that case, technically, all 3 of those are they're fine lists. Like
They're fine as lists. Yeah, as lists they're fine as long as you don't try to evaluate them deeply.
so, in that, so like I see what you're saying.
But
It's
when-
not strict because it's not.
When we build, okay, so the first example, we build a set out of the list with 1 and a 2 and an undefined in
Oh, I
it.
see.
And then as soon as it tries to order that set, it's going to
It's going to
screw up
blow
because
up.
undefined, it cannot order it, right?
Yeah.
Exactly.
Whereas if you have the second list, which is the list of lists, right?
Yeah.
Each of those in turn is a perfectly valid orderable list. I don't know what criteria set uses to order lists.
It's what criteria
But-
list use sort of.
It's alphabetical or
Yeah.
lexicographic.
Yep.
Wait,
So
alphabetical.
I mean lexicographic.
Oh.
Yeah. It's the same principle as alphabetical. So this would actually fail if instead of 3 undefined, it was 2 undefined, and then the other one was like 2, 1 or something. because then you'd be
Then would have to actually evaluate the second member of the list
exactly
in order to order it.
you'd be forcing it to evaluate an undefined. But in this particular case, it can order the elements without traversing the whole list. So it
Right.
never has to evaluate that undefined.
So list of 1, list of 2, list of 3, comma, undefined works, whereas list of 1, list of 2, list of 1, comma, undefined wouldn't work. And then obviously list of 1, list of 2, list of undefined wouldn't work either.
Right. Actually, the
No,
list.
that would work.
Actually, no. If you gave it a list of
List of
one,
undefined.
if you gave it a list with just 1 in it,
Yep.
and a list with just 2 in it, and a list with 1 and undefined in it, it would be okay. Because
It knows it has a second one.
yeah, I mean, it would say okay.
Oh, because
it can compare
it
them.
can compare it. No, it looks at the number of members. Then it's
No,
limited. Yeah.
It doesn't look at the number of members, but it would say, okay, the first one is 1 cons empty list.
Yep.
The other one is 1 cons something else that's a cons. And it
Ah,
wouldn't have to
actually
know what's
evaluate
in
what
the cons.
is.
Exactly.
Wait, so what would it be, I think you already asked this, what would it be if it was 1, 2, so the second one, a list of 1, a list of 2, and then a list of undefined? That would blow up.
That would blow up, yeah.
Okay.
Because it would have to compare the undefined
Right,
to
and then it's like
undefined.
that.
Because the set, when it builds up the set, it does order comparisons as necessary to figure out the structure. So it's strict in the structure. It's not necessarily strict in the leaves or in the values that are in the set. Data.map, that's the associative collection or the dict in Python. They're faster than association lists. Actually, that's not completely true. If you only have like 5 things, then an association list is actually faster. But once you have like 50 things, then the map is going to be faster. Your insertion, deletion, and lookup are log n time, just as with data.set. And here are some of the functions. You've got empty. That's an empty map. No word constraint because it's not. It doesn't need it, because it's just an empty map. Singleton, similar to the singleton set, takes your key and your value. Your value type is called A. From list builds up a map from an association list that does have the ORD constraint. Your keys have to be orderable. To list doesn't need the ORD constraint, and keys and LMs are just to get your list of keys or your list of values, and then there's size. And there's more. There's a lot more. We have lookup, which takes a K, that's your key, and the map, and returns maybe A, because it's going to return just V if there's a value V. It's going to return nothing if it's not found.
So nice. Better than throwing exception.
Exactly.
Jesus Christ. I hate
Exactly.
when dictionaries do that. It's one of my pet peeves.
It's awful, and Haskell doesn't do that.
Yeah, it's so nice.
But if you want Haskell to do that, you can make it do that using the bang operator, the infix bang, which even more confusingly, it reverses the argument order, so it takes the map first. You probably should not use bang, but it's there.
What does that dash partial mean on the right side?
It means it's a partial function, which means that some inputs it will fail.
Yeah, okay.
Total function means it will always return something valid. Partial means that it might throw an exception or go into an infinite loop.
This is better than the other.
I'm sorry?
One of those is-
That's true.
At least you get more immediate feedback.
Right, right.
Is that shown if, like, let's say you did a :T on the bang, would it tell you that it's partial?
No.
Okay, so that's just something you
No.
just gotta know.
Yeah, I mean, you can look it up in the documentation.
Sure. Okay.
Or in this case, you can tell, if you know that a map can be empty, then you know that it's partial, because you can have an empty map.
Yeah, there's definitely no K.
If you know how maths work, you can know that if you say, give me the thing in here, forcibly.
Well, the empty map is map KA for any K and any A. So and for any A, the value, okay, so this is diverging a little bit, but if you have something that is a list of A for all A, you know it's the empty list because any other list has, you know, something in it, and that something has a type. So the fact that it doesn't return a maybe A, but it returns an A no matter what that A is,
Oh,
means that it's a partial function because it could fail you.
gotcha.
There are, in fact, in Haskell, there's the ability to define an empty type, which is a type that has nothing in it. And you can use that return type to say, I don't intend for this thing to ever return. That's actually quite useful. There's also a thing called phantom types, which we may get into at the end of this course. But
I think a good thing for consistent behavior is default dictionaries. Like, this is a Python thing.
yeah,
A return, you always return a value of said type, like of a specific type, even if that value has to be this fallback.
well, lookup does the next best thing, which if it's not found, it just returns a nothing.
Yeah.
And lookup is what you should generally use. We have insert and delete, which insert and delete into the map. And we have alter, which takes a maybe A. It takes a function from maybe A to maybe A and a K. And what that does is it says, okay, at that K, apply this function to what you get when you look up. And if the function returns a nothing, then it's saying delete it. And if it returns a just, then it's saying put it there.
Yep.
What?
Okay, so
One more time.
alter is your map update function. You know, this is essentially the CRUD
Oh,
of maps.
I totally got you. It
And-
returns a maybe A because you might not, the result of that function might not be something to put back into the dictionary.
Yeah, the result of that function might be I want you to delete it.
Okay.
And then you have a nothing.
I got you.
So if you pass in a perfectly okay. So if you pass in a function and the K to alter, and well, I guess that
It's like
it's not gonna
saying,
do anything. Yeah.
it's like the equivalent in like a loose language of not returning something from a map function.
Yeah.
You return none, and it's
Yeah.
like, okay, this doesn't go back in.
Right.
Apply this transformation at this index, right? And the index doesn't exist. Well, fine, applied.
We have union, which takes two maps on the same key and the same value type, and it returns the key-wise union. I think it favors the first of the two sets. I'm pretty sure it does. I'd have to look that up. I just forgot because I never leave that to chance. You have union with, where you can specify how you want A's to be combined if the key is found in both maps. And then there's union with key, which allows you to pass in the key K to that function.
Why do you have the OR constraint on K?
Because the keys of the map are sorted. It's sorted by the key.
Right. But isn't that like inherent in it being a key for a map? Doesn't that need to be?
Well,
like a
map doesn't actually specify that something is ordered. It's only the functions on map because you can have a singular map.
Yeah. Okay.
And historically there were cases of data types that had constraints on them, but they took it out.
Okay.
And the reason they took it out was they said, well, I think the reason they took it out is because, I'm guessing here, but I think the reason that they took it out is because if you look at the set fold, for it to be a foldable type, it has to conform to the foldable type class.
Yep.
And the foldable type class doesn't care about ORD.
Okay.
So I think it just reduces the complexity.
I think in those functions cases, like you would say that a map should be able to merge any map with any other map, but like given that like you don't get the guarantee from either way because you could get two things that aren't orderable and you merge them.
Yeah.
And then you couldn't do that if they were two different keys.
Now, anytime you have a map with a non-ORD type, that's pathological. Like you just shouldn't use a map. Even if you're doing it, you should. But there's no reason a priori to say that the empty map of a non-ORD type is invalid. So, yeah. Here's an example of union with, where you have like a word count. So I'm just using a type synonym. Word count is a map of strings to integers. And then you can combine your word counts let's say you're doing some kind of map reduce, and obviously you want to union the two sets, and if you've seen 3 instances of the word the in the first set and 5 instances of the word the in the second set, then when you combine them, you say 3 plus 5, that's 8 instances. So that's an example. There's also merge with key. This is sort of the general merging function. I actually don't like this API, and I'll explain why I don't like it. But first I have to explain what it is. The reason I don't like it is it's just a little confusing. You give a function that says, the first function is what you do to merge. And remember, since it's returning a maybe, that's meaning that it might return a nothing and say, there is nothing at that key. But the first function is what you do when that key is found in both maps. The second is a function that's applied to the map of the map of things that are in the first map but not the second. So, and then the third argument is a function that you apply to the collection of things, or the map of things that are in the second map, that is the 5th argument, but not the first map, that is the 4th argument.
Sounds horrible.
It's a little confusing. So I would actually prefer an API like this, which is more comprehensible. You have one function, and it says, okay, at this key, if you maybe A, because it might be in the first map, it might not. Maybe B, because it might be in the second map, it might not. Obviously, you're not going to have a nothing for both cases, because that would be like the space of all keys that are included in neither. And it returns a maybe C, which means that, well, if it returns just C for some C, then it's...
You're basically saying, let me deal with all of that branching that you're having me do by passing you 4 functions. Like, I'll fucking deal with it.
Exactly. Exactly. You can actually write this on top of alternative merge. I don't know if this is or you can write this on top of merge with key. I don't know if it's as performant, but it can definitely be done. And you could probably write a more performant version of my alternative merge, but this is how I would have done it on top of the existing merge with key. So, do we have any questions?
Is that your kitty?
That is not my cat. My cat is well, actually, I think he's an internet star at this point. Omar watching. Omar. I have 2 cats, actually.
Like you are the internet star.
So this is Omar. That's not a very good picture of him. And then that's Henrietta.
Nice.
So I've got 2 cats. That's just I like black cats, so I decided to put a black cat there.
Yeah, so that guy's a black
I
guy.
have a pure black Maine Coon.
Nice.
Yeah.
Nice.
Maine Coon, like, you mean like the big ass Maine Coon?
She is of that breed, but she herself was the runt of the litter.
Okay.
And is a tiny little girl.
So she's
Well,
only
for a
like,
Maine, she's the size of a normal cat,
Okay.
but she's also a Maine Coon. And she is like,
We have a cat that is like basically, what's the name for them? They're like the American long-haired, basically. The really basic, adorable as fuck long-haired looking cats, like with the big hair coming out the ear. They look just like Maine Coons, except the problem is she's like the size of a large rat.
yeah,
She's very small. It's really adorable.
that's cute.
my cats are 11 pounds apiece, so they're pretty big.
Not that adorable.
I'm sorry?
Not that adorable.
Oh no, they are. They are.
It's weird for me when I see regular sized cats because like I forgot that cats are not as small as my cats. Like I see a normal cat, I'm like, what are you? You're huge. And I'm like, nope, they're not.
My cat plays fetch, which is
Yeah, dude, I didn't know they did that. I have one cat. Who does it. I'm
I
like,
have
what's
one.
wrong with you?
I have one. The other one, no.
That's kind of how it goes, right?
Yeah.
Yeah, the
That's
one's
exactly what
judging
it's
it.
like.
Oh, you're playing his games.
Oh man.
Michael, how much time do you have When do you have to get home?
Probably should leave in about 20 minutes. Why do you ask?
Just curious, because yeah, last time you had to take off, but you have time for questions though.
Oh yeah, I've got time for questions.
Cool.
So can I ask like a question like not related to this particular, but like
Of course.
Haskell? So how did you get involved in like Haskell? Like how did you realize that Haskell was the one true way and you were gonna do it for your whole life?
Did
Well-
somebody come door to door?
Is it the
People
one?
heard the good word
Yeah,
Haskell.
exactly.
I mean, first of all, I don't know that it is the one true way, and I don't know that I'm going to do it for my whole life because I'm only 32, and granted, in Silicon Valley, that's like 86, but everywhere else, it's
Yeah.
still kind of
Might as
young.
well just like I guess kill yourself, right?
But everywhere outside of California, it's still kind of young, and 30 years from now, there will be more languages. So I don't know what I'll be using 30 years from now. With regard to Haskell, I used OCaml in 2007, 2008.
Okay.
And at the time, Haskell's reputation was that it wasn't fast and that because of laziness, it was hard to reason about performance, which it's actually not that hard because Haskell is actually opt out with regard to laziness. You can opt out, and you usually do if you're writing high performance code, but you know, the default is non-strictness. Anyway, so I knew OCaml, and I knew that a lot of OCamlers had Haskell envy. They like type classes. OCaml, I think, is still a little better if you're just going to do all system programming all the time.
Okay.
But anyway, I got pulled into dynamic languages, and that was great too because I learned a lot. And I think everyone should spend at least a couple of years in a Lisp. So I learned Clojure. I took up Scala, which is interesting in its own right. And then I found out in 2014, when I was looking for jobs, that there was one company that was doing a lot of Haskell, and they were looking at me for their director of data science, which is even higher level than it sounds because this is the European system where director outranks VP.
Nice.
But they were kind of in a mess with regard to investor relations, and so they couldn't afford my relocation, and because it was an international relocation, it was like, well, that's not going to happen.
Yeah.
But I'd spent a month learning Haskell, and I was like, this is fast now. And I'd had some friends who had gotten into it and who were pushing me to learn it. So I started reading up on it, and it had come a long way. And I realized that of the mainstream offerings, it's probably the best for the kind of work I want to do. If I were a data analyst data scientist is such a weird term these days because, discussing data science is like discussing God. It's completely useless unless you define terms because people mean completely different things. Or like feminism, it's the same thing. Like it means different things to different
I
people.
always thought data science was just opening Excel on a Mac.
Nice. Nice. I mean, some people use data scientist to mean machine learning engineer, and some people use it as like a bullshit title to make, what you described, Excel on a map, sound sexier than it is.
I think those people diverge at interviews
Well,
or just resume screening. But
that's a long discussion for another time. Because I mean, you're absolutely right that like maybe 10% of people who call themselves data scientists know like. I feel like if you don't know what a convex optimization is, then that's fine.
Yeah.
Like a lot of people don't, but you're not a data scientist.
Yeah. Honestly, look, if I can be a programmer, then anybody can be a data scientist.
But anyway, if I were doing sort of like more fast cycle data sciencey stuff where I had to use data frames a lot, I'd be more inclined to use Python. I think that Python wins for the short-term projects. I think Clojure wins on the medium term, and I think Haskell wins on the long term. But given that I'm ancient, 32, I mean, I'm practically walking with a cane. I'm only interested in the long-term infrastructural stuff. So
You could be my older cousin.
I
Exactly.
mean, I'm actually older than you.
Oh, okay. Okay.
Dave.
Do you have a lawn? Do you tell people to get off it?
Yes, all the time. All the time.
No, Dave lives in a
Give-
condo, actually.
I'm getting very cantankerous in my own way.
Oh, dude, I was a curmudgeon at 15.
Oh, wow.
I was a curmudgeon before it was cool.
Nice. Curmudgeon hipster, I like. Alright, that's cool. So you do mainly like data science stuff then, like statistics-ish, mathy stuff.
It's an interest of mine for sure.
Okay.
It's not what I'm using Haskell for right now, but I would love to build out some, hardcore machine learning infrastructure.
Nice.
It's definitely a long-term interest,
That is my cue.
and I think Haskell is a good language for it.
I'll do that later.